Hey, good morning, everyone. Thank you for joining us, RC Design class on Monday. Really happy to see you all here. I see people are gradually coming in, and let's wait for a couple of minutes. First of all, I'd like to make a quick announcement. I have received all your exam number 2. I glanced through them and started grading yesterday, and I think we all did a good job, but there are a few minor mistakes actually regarding to the shear design portion, which I'll mention on Wednesday. And I will start, getting in touch with people that may have some troubles in getting the solutions to the exams, and we will briefly talk about that on Wednesday as well. And for your information, we will summarize all the grades this week in terms of quizzes and homeworks and the exam number 2. And we'll have an evaluation, kind of knowing where we're at and what we need to do. And I will also release a grading formula equation, basically, you can use to calculate your current standing, and we can communicate after that. All right. Okay, so that's about the second exam. And we didn't have homework last week, so we'll have it this week. So be prepared. And we talk about the design, well, actually the deflection for service design. So we're going to continue. Okay. So lecture 19, we're still gonna do the service design. And let me just put it here, lecture 19, and especially deflection. All right, especially deflection. Excuse me. All right. So a quick review what we have talked about before. Okay, what we have talked about before. So in terms of deflection, right? In terms of deflection, you can think of it. We draw the moment diagram. We draw the moment diagram, and we draw the curvature. Right? We draw the curvature. Okay. So when we have these, right? When we have these, our response in terms of the moment versus curvature response have 3 stages, right? Number 1, and then linear number 2, and eventually flatten out number 3. All right, flatten out number 3. And the reason why we have these 3 stages because the concrete went through different stress state. Okay, the concrete went through different stress state, and we know that from the past experience, crack occurs here for concrete. Okay, and then yielding occurs here at stage 3. All right. And we also introduce some of the critical concept, for example, the modular ratio, right? And this is defined as the ratio between the Young's modulus of steel, ES, and divided by Young's modulus of concrete, EC, okay? So let me just rewrite it in case some of you might have a problem with this, okay? And we know that this is roughly equal to 8. This is roughly equal to 8. And keep in mind that the concrete is C modulus Young's modulus equal to 57,000 square root of F prime C. Square root of F prime C. Okay, so this is what we talked about last time. And when we talk about deflection, right, we need a moment of inertia and the Young's modulus E. Okay, so we need EI to calculate the deflection. So EI is kind of like a bending rigidity. So you notice that E most likely will not change. Okay, E most likely will not change. That's just the concrete itself. What most likely going to change is the moment of inertia. Okay, moment of inertia. So as moment inertia I changes through different 3 stages, the whole deflection calculation are different. The deflection calculation are different. So I changes with respect to different stages, right? So with respect to stages. So that is the critical thing here. But for all intent and purpose in our design, okay, in our design, we only care about stage 1 and stage 2. We don't really care about deflection at stage 3. And the reason for that is at the stage 3, the beam is going through failure. The steel yielded, the concrete gradually become crushing. So we don't really care about deflection anymore. We don't really care about deflection anymore. So it is IGT, all right? And we call it IGT is stage 1 moment inertia, and ICR, which is stage 2 moment inertia, are the most concerned moment of inertia for calculation. We need to know how to do that. All right, so that's where we're at. And then continue. Let's talk about stage 1, right? So first of all, we call it stage 1 called uncracked elastic. Uncracked elastic. Meaning the section will not have crack in it. The concrete will not have crack in it. But the whole section remains elastic, right? The whole section remains elastic. So you take a look at the section, right? So it's a nice rectangular section, for example. And in this rectangular section, I have reinforcement at the bottom, say 3 reinforcement, and I have depths right here, D, and I have the height of the section H right here on the right hand side, and say the width is B. The width is B. Okay. And if I were to draw the stress distribution, since everything is linear, right? Since everything is elastic, right? So the stress distribution should follow the linear distribution and has a stress at top, concrete stress at the top, and concrete tensile stress at the bottom. Okay, so this is compression, and this is tension. All right, so that is a stress distribution. And if you really want to notice that this thing here, we talked about this before, is the concrete tensile strength, and happen to be 7.5 square root of prime C lambda. Okay, so this is the tensile strength of a concrete. All right, now if you look at the cross section here, I have a rectangular concrete section. I have reinforcement at the bottom. Because that these reinforcement have a higher Young's modulus. All right, so I have to convert that into concrete. Okay, so watch carefully. How do I convert that into concrete? Right. So first of all, I'm going to remove these reinforcement. When I remove them, I left with 3 holes. Right, left with 3 holes, and these are empties now. Put the bar out basically. Right? And then I fill them back in with concrete, right? I fill them back in with concrete. And in addition, I also add another 2 little wings on the side. I add the 2 little wings on the side, okay? Because I fill it up with concrete now, I fill them up with concrete now. So this in the holes right here is AS, right? That's the area of steel, basically, equivalent to the area of steel, right? And outside here become N minus 1 AS, okay? And divided by 2, and this is N minus 1 AS divided by 2. If I add them up together, right? Add them up together, so this gives me N AS. And this is a converted area from steel. Okay, what essentially I did is I removed the steel, converted back in concrete, and filled it back into the section. Okay, now after I done this, I look at the section again. I realize that my section has been transformed. Okay, so this is called transformation, and this is my transformed section. Right? So in the composite section, you learn from mechanics material, you probably experience something similar. But right now, after I did the conversion, I have a concrete beam, looks no longer as rectangular, but a rectangular with small wings on the side, And knowing that this is N minus 1 AS. Okay. Outside 2 wings add up together, give me the area N minus 1 AS. And it's very critical that you know this. The center of these wings, right? The center of these wings still stays the same level as the bars before. So that is D, depth D. Okay, depth D. All right, so I look at this section, right? I say I want to find out the centroid of the section first, right? So centroid of the section, let's say, is y bar. Okay, y bar is the centroid, and according to this, right, it's gonna sit a little bit lower, sits a little bit lower than half h. Okay, and I'm gonna call it y bar top because it's with respect to the top line here. All right, so how do I find the center? How do I find center? Okay, now I divide these two pieces, right? I divide this into two pieces. The major rectangular piece is called 1, and the little wings called 2. Okay, so if I do that, then y top essentially using that equation is the first static moment, a 1 area of 1 multiplied y center distance between the center of 1 to the top line plus a 2 multiplied y 2 and divided by the total area, which is a1 and a2. So that's how I find y top, right? So naturally, area of a1 equal to bh. That's the area, right? So this is b and this is h. Easy, okay? And then y1, what is this distance between the center of piece 1 to the top line, right? So if I look at this rectangular, it's very simple, right? It just half h, middle of it. Then a2, we know the area, which is n minus 1 as. And what is n again? N equal to es over ec, by the way. Okay, so y2, which is the distance between the centroid of 2, which is right here, right, to the top, right, to the top, which means it is just d. Okay, that is the distance of y2. Right? So with this, I just need to find out the moment of inertia and be careful the notation, right? Be careful the notation here on the right hand side, the subscripts called G, which means G the gross, the total, right? And T means transformed, right? Transformed. So this should equal to the moment inertia of 1 plus moment inertia of 2. Okay. So that is how we calculate moment inertia for this. This is stage 1, by the way, okay? Stage 1, still uncracked elastic section, uncracked elastic section, okay? So that's how we're gonna do it. But for the moment inertia, you know that since the shape is irregular, right? Shape is irregular, we're going to use the tabulated manner to calculate moment inertia, right? So how to do that? We're going to use the parallel axis and establish the table right here. So let me call this A, which is the area, and then D, which is the distance between the centers, right? So distance between the centers. Okay. And then I have I naught, which is the moment inertia with respect to its own axis, and total moment of inertia, total moment inertia. Okay. Let me move this a little bit lower so I can see the table better. Matter of fact, let me use the second page here. Okay. So to create this little table, I need to fill them in, right? So I have to do the two parts. Okay. Two parts. Now this is part 1, which is the rectangular section, and part 2, which is the little wings on the sides. Okay. So let's take a look, right? For area, right? For area 1 here, I want to find area, right? And this is A1, right? A1, so this is BH. Okay. Now A2, which is N minus 1 multiplied by AS. Okay. Distance D, right? Distance D is the center of 1 to the center of the whole thing, right? Center of the whole thing, right? So how do I do this? This is Y top basically minus h over 2. Okay, that is the distance between the center of 1 and to the centroid of the whole thing, centroid of the whole thing. And here is d minus y top. All right. Now for its own moment inertia for 1, right? For 1, it's just basically the rectangular again, rectangular again. Okay, so this we call it 1 over 12 bh cubed. 1 over 12 bh cubed. Okay, for 2 has to be little strips, right? Has to be that little strips. So say that, oh, okay, it's going to be 1/12, and whole width, we don't know the width, just put a question mark here, but it's going to be very tiny strips, right? And let's call the tiny strip to be a t. Okay, so this is t to the power of 3, power of 3. All right, so this is a little bit awkward because I don't know the width of this whole section, n minus 1 as. What I will do is that I will notice the height of the strip is very small. Okay, it's very small. You say how? Because we can make it small to ensure that stay the same level of steel. If I do that, which is the case, and this becomes negligible, almost 0. Why is that? Because t is almost 0, so t to the power of 3 is almost 0. Okay, so this can simplify our process quite a bit, quite a bit. Okay, so now that is 0. Then to summarize the table, the total moment inertia for 1, just add them up together, right? That would equal to I naught, which is this fellow here, plus A1 D1 squared. Okay, this is the parallel theorem. This is the parallel theorem. Okay, and for this, since I not 2, this is 0, right? So 0 plus a 2 d2 squared. All right, so that's for section 2. That's for section 2. Okay, so with this, IGT equal to I1 plus I2, and this is I1, this is I2. Just add them together, right? So this equal to I naught at 1 plus, and let me just write it out, okay? I naught plus, I naught 1 is 1/12 BH cube plus A1 D1. So this is A1 BH. By the way, this is A1, okay? And D1 bar squared, basically Y top minus half H squared, okay? And plus 0, because this is 0 and there's no moment inertia with respect to itself, and plus a2 d2 squared. A2 is what? Is n minus 1 as, that is d2, sorry, a2, and distance is d minus y top squared. All right, so that is the IGT for uncracked elastic section, IGT for uncracked and elastic section. Okay. All right, so you say, Bob, this is complicated. Do I need to remember this equation? You don't. You just have to follow the way how we compute it using this table here, so you know how to do that. Okay, but essentially, let me put this straight. And this is the equation for the moment inertia for the uncracked elastic stage, uncracked elastic stage. All right, so now I know IGT, which is this fellow here. I want to know stresses. I want to know stresses in the section. So what about stresses in the section? Okay, so to know the stress in the section, right, we need to have a moment. We need to have the moment. So given the moment, right, given the moment, okay, we know that the concrete compressive stress is what? Is FCC, concrete compressive stress, equal to the moment m multiplied y top, y bar top, divided by the distance, right? Sorry, divided by the moment inertia, right? IGT. Okay, and that is the stress. And you may wonder, where is it at, right? So on this transform section, I'm just going to use this to show you, right? This is transform section. FCC is compressive, right? So right here, this line right here, compressive stress. Okay, so that is for compression. Now for tensile stress in concrete. Okay, we're talking about steel in concrete. Okay, so this FCT equal to what? Equal to the moment m multiplied by distance, which is h minus y top. Okay, divided by IGT. Okay, IGT. And you may ask, where is it at, right? So again, let's copy this little image here. Oops. And paste it here. So it's tensile, right? And we all know that tensile here is at the bottom. Is the bottom. And since it is concrete, okay, since it's concrete, so it's right here. So this is FCT. And this distance h minus y top is because y top is somewhere here. Okay. And the distance between that to the bottom here is is h minus y top. H minus y top. All right. So that is for the tensile stress, right? And last but not least, how about the tensile stress in the steel? How about the tensile stress in steel? All right. So the tensile stress in steel and Fs should be same moment multiplied distance, right? Now the distance
Hey,
become
Professor,
d. Yes.
sorry to interject real quick, but you have someone who's in the waiting room.
Oh yeah. Thank you. And now the stress in the steel m moment here multiplied distance, which is depth d minus the y top. Okay, minus the y top, and then divided by IGT. Okay, so that is the stress in the steel. But this is the transformed section, right? Transformed section. So this is not the real stress in the steel. Real stress in steel. So how do we transform the stress into the stress in the steel? We have to multiply the modulus ratio n. Okay, multiply the modulus ratio n back. Okay. All right. So if you forgot about this, you can go back to see from mechanics material. That's how we compute the composite stress. Composite stress. Okay. So for this, right, let me copy this section right here. Okay, copy this section right here and put it right here. Just get this thing out of the way. And for steel, right, for steel, it's no longer at the bottom here. It's right here at this point, the level of the reinforcement, and the distance here is d minus y top, right? But don't forget, when you calculate the composite section, right, for stress composite section, you use the composite section moment of inertia, but multiply back the modular ratio. Okay, so this is steel. All right, okay. So now this is the stress. This is the stress in the steel, right? And we have find out a way to compute the moment inertia for the uncracked elastic section and the corresponding compressive stress, tensile stress in concrete, and tensile stress in steel. All right. And again, you might need to remember these equations here, here, here. Now you don't have to remember this equation here, but need to know how to compute or how to get here from this table here. Okay. All right. So this is stage one. That means the whole thing stays elastic and I can compute my moment inertia and then find out my deflection, okay, which we'll talk about next lecture. But how about stage two? Stage two. And we call it cracked elastic. Cracked elastic. Right? These two words are usually contradicting each other. When a cracked, it lost its own properties, right? And why it's still elastic, right? So let's take a look at it. When I have a section, right, like this, a rectangular section, with a reinforcement at the bottom here, reinforcement at the bottom here, right? And then I know the strain distribution in the section, stress distribution before in stage one is fine, but in stage two, I have my beam cracked already, okay? So I have a strain that is still elastic, stress not so much, okay? But in terms of strain, the top is the compressive strain in the concrete. The bottom here should be the strain in the steel, all right? And you know that at a certain level, this right here has reached the tensile strain for concrete. Hence, it cracked. Okay, once it cracked, what happened is that I lost my stress or strength in the concrete tension. So what I will do is I will have this portion, but in reality, after crack, they're gone. Okay, after crack, they're gone. Has no more the tensile stress from the concrete. Okay, now what I left with is only the compressive stress in the concrete. Okay, and when I say elastic, it's because I still assume it follows the linear distribution. So that's why I call it elastic. All right. So at this stage, the stress redistribute. The stress redistribute. And once it redistributed, I have to redraw my stress distribution. I still have my compressive stress part. Okay. And then the tension will be carried by steel only. Okay. The tension will carry it by steel only. Okay. Now this becomes interesting because now with this, I have to compute my compressive zone. And I would say my compressive zone is some number in the form of KD, where K is the coefficient, D is the total depth. All right. And I will assume, and again, this is all under assumption that I will assume the whole concrete compression force is acted on a distance a third of KD away, distance a third of KD away. And that is my compressive forces. Compressive forces. Okay. And now the distance between the compression and tension here is the lever arm GD. It's the lever arm GD. So that is new stress distribution within the cracked section. Within the cracked section. All right. So here, this is a little bit hard to do. Why? Because now I'm looking at the section, it looks like this now. I only have a top compression part still remains for concrete. The bottom part gone away because they are cracked. And for the lower part now, I only have the tensile stress from steel, which I can now convert this thing to be NAS, right? NAS. You may ask, okay, where is that -1? Because we don't have to fill the hole back in because there's no concrete in this area anymore. So I just have N minus multiplied AS left. All right. So just to give you a residual image, this is where the cross section of concrete used to be. And now I only have these two parts. Okay. Again, to find out moment inertia for this fellow here, find out moment inertia for this fellow here, I need to name one and name two. Two pieces again. All right. And we don't know exactly what it is, but I would say that this is KD. The compressive zone is KD. Okay. And I have a width of B for the section, and I have 2, and I know the depths between the center of 2, okay, and the top line is D. So this is all I know, okay, all I know. And if I want to add, I also know this is D minus KD, okay, D minus KD. So that's all I know. All right, so the game is, what is K, right? What is K? K is just some coefficient I made it up, invented. I don't know what is K. Okay, I don't know what is K. So how do I get K, right? How do I get K is I know that I have to get the center line for the whole section using that equation, right? Y bar equal to Y1 A1 plus Y2 A2 divided by A1 A2. So without going through the detailed process, when I do that, I can actually get equation for K. I can get equation for K. All right, and solve for K, I can find out K, and K is in terms an equation, and this I need you guys to remember. Sorry, let me use different color, okay? Need you guys to remember this. K equal to a square root of 2 rho, be careful, I'll explain this, okay? N, which is modulus ratio, and this is ES over EC, by the way. And then plus a rho N squared. Okay, this is all under the square root sign minus rho n. Okay, And I need you to remember this equation. Okay, remember this equation. We need it for the exam. Okay, so this is the K. And also Y center of the whole section equal to KD. Okay, so need to remember these two. All right, need to remember these two. And now rho. Rho is the reinforcement ratio. It's simply defined as AS, reinforcement in steel, divided by area of the cross section BD here. Area of the cross section BD here. Okay, so that is how we compute the cross section, right? Cross section for the cracked elastic stage. Cracked elastic stage. Okay. All right. So this gives me the moment inertia. How? This is how. I have now two pieces, right? And to find the moment inertia, I still need to do my table thing here, right? So A area and D bar, which is distance between centers, and I naught moment inertia, and then what is it? What else we need? Let me see here. And sum the whole thing sigma I. Okay. Let me rotate a little bit so you can see the section where we're doing it. Okay. So A, which is area, right? Again, let me divide the table into piece one, piece two. So piece one, the area equal to B multiplied by KD, isn't it? That is the area. And here, the bar, which means the distance between the centroid of this fellow here to the neutral axis, right? To the neutral axis. By the way, this is where the neutral axis is at, or center line is at. Okay, so that, ladies and gentlemen, is simply what? Simply KD minus half KD, isn't it? Half KD, isn't it? So essentially just the half of it. So let me remove that, and that is that. Now, I naught is 1 over 12, B, which is the width, and KD cube, KD cube. All right, to sum it, so this is 1 over 12, B, KD cube plus an area, which is B, KD, and the distance is KD over 2 squared. That is the moment inertia for piece 1. Okay, for 2, this is straightforward, NAS. Distance, this is basically D minus KD. And I naught, remember, the tiny strip T almost equal to 0, so this is 0. So add them together, this is NAS minus D KD squared. Okay. Now with this, the critical moment inertia is simply adding them all together. So 1 over 12 BKD cube plus BKD 4 KD squared. So let me simplify this. Equal to BK squared D cube over 4 plus NAS D squared. Take the whole thing out, 1 minus K squared. All right, so that, ladies and gentlemen, is my ICR. Okay, that is the moment inertia for the crack section. Moment inertia for the crack section. All right, then again, back to the question, what about the stresses? What about the stresses for this section? Right? So we have introduced the concrete compressive stress CC, right? So you know that. So for the moment, and this become 2m divided by JD, okay, which is distance, right? And then KD multiplied by B. Okay, just have to remember this, right? And this is the stress in the steel. Okay, you may ask, what happened to stress in the concrete? It cracked. It doesn't have any stress in concrete. All right, only have stress in steel. And now that it becomes AM divided by AS, okay, divided by AS and JD. Okay, and JD is the distance between the compression center of compression to the tensile forces, and that equal to D multiplied by bracket 1 minus K divided by 3. And for all these equations, you just need to remember it. Okay, just need to remember those. All right. So that, ladies and gentlemen, is the stresses for the cracked elastic. Cracked elastic. So I just want to emphasize when we say crack elastic, right? The definition elastic, meaning the stress in the compressive zone of the concrete is elastic, meaning it's linear. All right, and that's the reason why we have elastic in it. Well, reason we have elastic in it. Okay. All right, so this is all the concept to find the moment inertia for the uncracked and cracked section, stage 1 and 2. All right, so just want to pause here. Do you have any questions so far on the concept? Anything, folks? Anything? All
I'm
right.
good.
This is might be thanks, Luis, and this is might be a little bit boring. And the most important thing is that for the uncracked section, there's more rationale to follow, right? And you probably seen this before. It's just a composite action, right? Composite section. But the only problem is that for the other one, cracked elastic, for the cracked elastic, right? You have just to follow this equation through, follow through these equations. So do have to remember, you do have to remember how to use these equations. Okay. All right. Now, with all these concepts covered, let's take a look at an example. Okay. Let's take a look at an example. All right. So the example is to determine the IGT, which is a transformed moment inertia, okay, and stresses. Okay, for a section under a bending moment, okay, section under a bending moment, that is M moment equal to 45. Oh, so let's start with the lower number, 45 kips foot. Okay, and this is problem number A, first part. Okay, problem number B, and bump up to 90 kip foot. Bump up 90 kip foot. And the parameters for concrete is 4 KSI concrete. Okay, and the tensile strength FR 7.5 square root of F prime C. Okay, and let me tell you already so you don't have to compute it. This is 475 PSI. Okay, PSI. All right, and the yield strength for the steel Fy equal to a 60 KSI. Okay, and the section is lo and behold very classic rectangular section, has bars underneath it right here, 1, 2, 3, and just say 3 number 8, 3 number 8, and the height of it equal to 25 inches. Okay, depth of it 23, and concrete cover 2 inches, and the width is 10 inches. Pretty small section, right? Probably just the over shelf beam. Okay, so for this, right, let's do it. So solve for this number 1 moment equal to 45 kip foot. Okay, kip foot. All right. So it was asking us to find IGT is definitely stage 1, right? So stage 1 uncracked elastic. Stage 1 uncracked elastic. Okay. Now for this stage, right, how do we do it? How do we do it? We need to take a look at the section first. Need to take a look at the section first. So the section looks like this, and I just have to do a conversion. And we said by adding 2 little wings on the side, 2 little wings on the side, and this is definitely in the middle of it, but this is n minus 1 as, right? N minus 1 as. Okay, and now with this, first thing is I want to, sorry, folks. I want to find out n, which is modular ratio, right? Should equal to a ES, sorry, ES over EC, ES over EC, and that is 29,000, sorry, 290,000 PSI. Wait a minute, let me see, 290 KSI, yeah, PSI divided by the concrete, which is 57,000 square root of 4,000 psi. Okay, and I found this ratio to be roughly at 8. So this is roughly equal to 8. All right, and now n minus 1 multiplied by as equal to 7 times as. So 3 number 8 bars, right, is 0.79 inch squared per bar. So have this number to be 16.59 inch squared. And that is the converted steel. Okay, that is the converted steel. All right, so first thing first, I need to find out the centroid, which is neutral axis. I need to find a y top. All right, and remember it's equal to sigma. Well, let me use that more simpler form. A1, y1, a2, y2 divided by a1 plus a2. Okay, all right, so put them in. A1 BH, right, which is B 10 inches, H 25 inches. Y1 is the distance, right? So if I call the center plug 1, this is 2. So the distance, right, between the center of the block 1 to the top right here is half H. So 25 inch divided by 2. Okay, plus a 1 that is 16.59 inch square. I just calculated. Okay, multiply the distance, which is y2. What is y2? Here is between that. So the whole thing this here is D, right? So this is D 23 inches, right? So that is the distance. And remember, everything when I talk about y top is referring to the distance, right? Refer somewhere. Let me put this out here. It's somewhere here with respect to the top reference line here. With respect to the top reference line here. Okay. So the total area equal to a 1025 plus a 16.59 inch squared, right? So you plug the number, and I got this number to be 13.2 inches as the distance from the top to the centroid of the whole section. Okay, all right. So how to calculate IGT, right? Then we use that table, remember? Use that table. So I'm gonna put A here and distance Y, D bar from here. And then I have, just put them separately a little bit away from each other. And then I have I naught and sigma I. Use that table. Okay. And then again, let's put them here. So this is 1. This is 2. Very easy. Now A1 is what? This. So 250 inches squared. Happy about it. 16.59 inch squared, which is N1 minus AS, A2. I'm okay. Distance, D bar for 1, right? For 1. And that is Y bar top minus, what is that? D half H. Okay, half H. So that is equal to 13.2 inch minus half H. H is 25, so 25 divided by 2. Okay, I naught 1 over 12 BH cube, so equal to 1 over 12 B, 10 inches. H, 25 inch to the 3 power of 3 cube. Okay, and sigma I basically add up together, right? And then here for the bottom one, right? For the bottom one, what is my area? Is 16.59 inches. What is the distance? Is D minus Y top. So D equal to a 23 inch minus Y top 13.2 inch. Okay, and this is 9.8 inch. 9.8 inch. All right. Now for this I naught, okay, it's 0, isn't it? 0. There's no I naught, right? For the sigma I here for 1, that is 1 over 12 here, multiplied by 10, multiplied by 25 to the cube, plus AD squared. So 250 D squared, that is 13.2 minus 25 divided by 2 squared. Okay. Now for this fellow here, I have 0, right? So 0 plus this here, so 16.59 multiplied distance 23 minus 13.2, which is, sorry, I already have the number calculated out, I forgot. This is 9.8, so 9.8 squared. Okay, all right. Okay, so that is my moment inertia for two pieces, for the two pieces. And then I sum them up together, right? So sigma I, summing this up together. So this fellow plus this fellow here, I have my total to be IGT of 1, 4. So IGT equal to that, equal to 1, 4, 7, 3, 7, and inch to the power 4. Okay, inch to the power 4. And that is my IGT. Okay. All right. Okay, I believe I'm running out of time, so I'm just gonna stop here. This is a good point to stop. And I will see you on Wednesday. All right. If you have any questions, you can ask now or stay behind. If not, I'll see you on Wednesday. Louis, we might need to talk, so you might want to stay a little bit. Rest of us have a question, please pop up now or stay behind. All right. Thanks, and I'll see you on Wednesday.
I have a question.
Go ahead.
So is there a